Is Andrey Pravdivtsev, who will be talking about unraveling SABRE with high field cycling from 10 nanotesla to 9.4 Tesla. Please, Andrey.
Dear everyone, dear committee members, dear committee, I'm happy for the opportunity to present our work. I'm actually excited to present this because it's somewhat a long-lasting project. It's maybe over 6 years of different tries to polarize some molecules, and will wrap it around in this very short promotional talk. But first, I just want to say that we are rather young lab in Kiel, so it's north of Germany. We have brilliant students who are doing pharmacy, who are doing DNP, SABRE, and FIB, and I will discuss here a few machines which we developed or we bought and we use them. So if you want to join us, feel free to write me. We have always opportunity to host you or work with you here. We have few open positions, so please apply. And this device I will show you, and actually in this talk will be quite a bit things polarized with DNP, but I think it doesn't matter how we polarize some things because at the end we are both trying to improve our hyperpolarization and we can learn from both approaches at the same time. About 6 years ago, I was curious to polarize nicotinamide because nicotinamide is in the center of very diverse metabolic reaction pathways. It goes to methylnicotinamide, nicotinamide riboside, mononucleotide, NAD+, and NADH are all involved here. So we had hypothesis that it can be used for cancer or inflammatory diagnosis. And first, to check this, we said, okay, let's hyperpolarize it. And the other important aspect of N15, especially of N15 nicotinamide, that the chemical shift dispersion is huge. So we can distinguish molecules because usually the chemical shift difference is more than 20 ppms, which is make it very practical for imaging due to this sufficient resolution. So we said, okay, it's good that nicotinamide was hyperpolarized before. We will not invent anything. We will just repeat what other people did. We will synthesize the molecule the same way. We started an experiment. We get the NMR machine. It's not actually a picture from our lab, but it looked quite similar at those days. Then we bought the twin leaf, a high pressure NMR tube. We placed it somewhere here on the bench. And then it manually started to shuttle the tube from the bench to the NMR spectrometer. And we were doing this for a couple of weeks. Then we had very unreproducible hyperpolarization from the same sample. So polarization varied from 0 to a couple of % polarization points. It depended really how well you move the sample. Then we said, okay, let's put the electromagnet, like about 10 millitesla magnet, around the tube and then move it between the low field and high field in this electromagnet. It didn't help. So actually, we never published this data, and I gave up at some point to hyperpolarize it with SABRE. And at the same time, we get the DNP polarizer, and I thought, okay, it's actually an amazing tool because in SABRE, we polarize everything in methanol, and here everything will be in water. So we don't have to even purify it. We have already everything, and we can test it immediately in our living organisms, which we have already prepared. So we hyperpolarize it to 15% in the first round at basic pH, but this we could not use. And then we started to work in neutral pH, and we again had any hyperpolarization whatsoever. So we hyperpolarize it the same way, but if we dissolve it at different pH, we have no polarization. So when we realized, okay, let's test the hypothesis. Let's see if something is important about low field pH. We hyperpolarize it, then dissolve it at basic pH. Then we went to the NMR spectrometer. And if we add acids in the side of the spectrometer, then we can retain polarization. But if we do it outside, there is no polarization again. So it means that something with low field and neutral pH for nicotinamide is very, very important. So we were thinking maybe this is the problem. We even estimated with a manual transfer the T1, and we get it about 1 second T1 of nicotinamide and 15 nicotinamide at low fields. So usually if you think that N15 has very long T1, but in fact some N15 nuclei have rather short T1, especially at low fields. So then this is the example of experiment of nicotinamide. After 18 seconds of transferring, we can transfer even at half Tesla Halbach magnet, at 1 Tesla Halbach magnet. It's actually not working. And then we thought, okay, let's check another hypothesis. Maybe it's interaction of this nitrogen with something which kills the polarization. We synthesized the methyl nicotinamide, and actually it worked perfectly. It has very long T1, polarization does not affected by pH, was very easy. So it means that indeed the N15 of nicotinamide is different from many other N15s which are exposed. At the same time, when we was developing, we started to build the high field, the shuttling system, like you see here on the slide, and we tried to publish it in the good details, so you can see on archive the blueprints and the 3D printed components. And actually, it took some time for us to develop it because you see we made the different design. Our seating is actually very short, so it ends here, and we could not use the straight rails, for example, like other people do, because we didn't have space for this. That's why we invented this flexible gear rods, which the gear rod is actually goes like this, curves, and then goes down. And this allowed us to shuttle the sample up and down. Now we use 1 second shuttling time, which is sufficient for SABRE experiments and many others. Here I show how we actually designed it. So we first made the 3D image of the mass spectrometer, then we decided everything in CAD, and then assemble it in our office. So this is assembly of the shelf and the guiding track. Then we have a center tower with the shield and the stepper motor. And here you can see the big button to switch off the shuttling. Then we carried it between offices. And actually, to my big surprise, it worked from the first point. We didn't have to adjust anything. We just connected to the transportation logs here, and it worked straight away. Here you can see how it looks in real time, in real life. And this is the design. It consists of like every other systems with the transfer system, then the magnetic shield. Inside we have electromagnet, which allows us to change the magnetic field between few milliteslas to 20 milliteslas. And then we have the shield, which allows us to do the SABRE sheet experiments. And we have the system, and I believe I want to show you how it works as well. So you can see the shuttling. Here we have constant logs of all experiments. On the right side, you see the track is moving. So it worked, and then we had a problem that we need to somehow shim the low magnetic field here. And what we thought of making the process automatic so that we don't have to shim it ourselves each time. And our proposal was following. So this is the field we measured along the twin leaf bore. And the field was inhomogeneous. And then twin leaf actually has nine shim coils. What we did, we measured the field from each of these coils. Then we calibrated the field profile from the coils. And now you can just use these profiles to shim your profile. So you have to measure the profile, these 9 shimming profiles, and then you can do minimization algorithm to make the field as homogeneous as possible. So we achieved rather low fields here. The black one is 10 nanotesla, and the sample size is relatively small. So we had below, 11 nanotesla standard deviation for the field there. So with this, we can now automatically shim the field before doing SABRE sheet experiments or other low field experiments. And then we measured again nicotinamide. So we came to nicotinamide and measured T1 relaxation as a function of time. So if you imagine just simple nicotinamide, dissolve it in water, you have relaxation time at low fields below 2 seconds. So it means that our shuttling with the SABRE, which we had before, actually could be explained by these problems could be explained by fast relaxation time. So if the T1 is comparable to the transfer time, it could explain that we had more than 100% standard deviation in our experiments. But then we found that if you add some molecules, like here we found that if you just add more nicotinamide, the T1 can increase. So the low field T1 is dependent on the actual sample composition. So we found several molecules which can be added to nicotinamide to prolong that relaxation time of the nicotinamide. And now quickly I will switch to I think I have 2 minutes. So we started the pyruvate as well with the same system, and this maybe could be interesting for most of you because we studied pyruvate and we found the composition for the pyruvate such that the relaxation is more than 4 minutes at low fields, so carbon-14 T1 relaxation of pyruvate. And a few last slides about SABRE, as it was discussed. So we have SABRE system, we have our shuttling device, and then we measured SABRE sheet. And we observed this asymmetric profile, although in theory it expected to be symmetric. So in fact, some other people like Thomas observed a similar curves. And actually we thought, but we can do a little trick. So we can do SABRE sheets, we can apply magnetic field right after we stop doing SABRE sheets, we switch magnetic field, and then with electromagnet, and then we do shuttling. So this way we can avoid the zero crossing, and we can have almost perfectly symmetric SABRE sheet polarization profile. And the last but not the least is with having high polarized with SABRE sample, we can now shuttle it to higher field. We can manipulate it, for example, using selective RF pulses, then apply variable delays, and we can measure the exchange rate between bound and free forms of pyruvate or other components. Here's the example of pyruvate, and this way you can measure exchange rates. You can measure dissociation and association rates. And actually, we compared this with the experiment we did before at higher fields without using any field cycling systems, and the results are rather comparable. But SABRE sheets uniquely provides higher polarization than, for example, SABRE INEPT, which we used before. And with this, I would like to thank you for your attention and welcome to Kiel.
Thank you very much, Andrey, for discussion and explanation of your wonderful system. So we have one question in the Q&A box from Alexei Kirutin, and I guess some people have similar questions. Andrey, did you find a reason for short T1 on nicotinamide at low field?
All right, so what we think it is, there could be several reasons, but we think one of the most possible is the rapid hydrogen exchange. So if you have hydrogen, which is binding directly to nitrogen and exchanging with a rate of few thousand hertz, then at these frequencies and below, the relaxation rate will be faster. It will be very fast.
And maybe a brief question. Can you explain how can you increase T1 of pyruvate to 4 minutes in short?
In short, so we found that there are few things are important. So we started to address them. So first, it's important to have buffer. Without buffer, you cannot have long T1. Then degassing of water. And then after this, you have already T1 of about 3 minutes. And then the last thing is the duration of a methyl group will be important, because normally it's not important for you at all, because the contribution is tiny. But when you're at 3 minutes, then the duration is so important that you can get another 1 minute.
Thank you very much. And I guess we can give a speaker one round of applause again.